So our speaker today is our very own Reza Haffari, who's one of our small numbers of natural language folks here in Monash. He'll be talking about learning deep neural networks with minimal supervision. Just a comment, one thing I learned probably about 5-10 years ago is that the natural language people who do machine learning are really good at machine learning, and Reza here is one of those examples. So, thank you.
Thanks, Ray, and thanks all for coming to my talk. So, what I'm going to do is to talk about some recent work that we have been doing, and I'm going to focus on 2 specific pieces of works, and don't talk about so many other interesting things that we do. So, specifically, what I'm going to do is to talk, how to train, neural networks with minimal supervision. So you may have noticed that deep learning and deep neural networks have revolutionized, many fields in science and engineering. So, for example, when you talk to your Android, i.e. when the speech recognition system tries to recognize your voice, the underlying system is based on deep learning nowadays. When you use Google Translate to translate from one language to another, the underlying model is a neural network-based model. When you do image classification on your Facebook, and of course, here is a more recent and more serious application, which is self-driving cars. So deep neural networks are basically not new. They have been around for so many years, for decades. You may wonder why they have been so successful recently. So first of all, one of the big factors in their success is access to fast computational devices these days, like GPUs. The other one is accessing to big data for the problems that we are dealing with these days. And once you have these 2 factors, you can just design a very, very big model and train it successfully. So this is essentially what's happening in the field. However, when you design your model, you have to be careful to kind of design it, appropriately for the task at hand. So some people, try to highlight the importance of architecture design by comparing it to traditional feature engineering step in building statistical models. So what I'm going to do is to kind of talk about some controversial issues. So I'm going to compare human intelligence with machine intelligence. So I want to argue that so far in machine learning, we have been mainly interested in pattern recognition. And pattern recognition, basically the pattern recognition approach leads to training your models for a very specific task at hand by giving your model an objective view of the world. For example, when you want to design a chess player, can I have some water if possible? Thanks. So when you want to design a chess player, what you do is you define the rules of chess, very cleanly for your computer, for your machine, and then what your machine does is probably, smartly searches for the best move, for the best next move, given that very clean specification of the problem. So this basically is rooted to rationalism, to science, which goes back 2,000 years ago, or several thousand years ago. So in that sense, machines are much better than human in those specific tasks. So think about, Kasparov, and Deep Blue System which defeated Kasparov in chess, and so many other success stories. So what I'm going to argue is that this is far from human intelligence, because one important aspect of human intelligence is being able to do several tasks successfully. And so as human, we can basically drive our cars, we can think about solutions for hard problems, we can cook, we can, teach, we can study, we can do so many different things. So, what's specific about this, this kind of intelligence is that, we kind of realize this intelligence by being in the world and by interacting with elements in the world, right? So this is, some recent work in philosophy, for example, Heidegger highlights, the importance of being in the world. So I'm going to argue, based on the same token, that human language understanding is hard. So why? Because if you think about language, it's a device, it's a subjective device that you use to communicate your ideas. So inherently, language is developed by being in the world, right? So, hence, it belongs to this, category of problems for, for intelligence, which basically is really hard. So to basically realize how hard is language, think about, several phenomena in language, for example, metaphor, sarcasm, ambiguity, and etc. So it even becomes harder for the machines to do, language understanding for situations where, the supervision is minimal. For example, consider a child learning the language. So presumably, the child doesn't have any notion of context-free grammar as, Chomsky proposed for syntax. In their head to kind of being able to glue together the words into well-formed sentences. So this is, if we want to mimic, the child language acquisition and learning, this is gonna be even harder for machines. So my goal in this project is tackling the following question. So can we basically teach deep neural networks to learn when the supervision is minimal? Right? So not only it has scientific merits, but it's also a very important practical problem, because for so many natural language understanding problems, we don't have gigantic amount of annotated data. All right, so the question is, why can children learn language with minimal supervision? So I'm going to mention two specific explanations. I will build up, our ideas based on these two explanations later. So the first explanation is that babies or children are able to acquire, language faculty because, there are some structural biases in the brain. Right? So this is something that Chomsky denotes as the innate structural prior, which basically can be resulted, in human genetic code by evolution. The other, possible explanation is that, the fact that as human we can do different things might actually help us to learn, new things. Right? So imagine, I'm good at, imagine a baby which is good at, detecting objects. The babies have good vision kind of capability, and, and other sensory inputs as well. Maybe, the knowledge learned from vision and, speech and other, sensory input may help the babies to learn language easier and better and faster, right? So this is something which is the root of a research topic which looks for general artificial intelligence recently as well. So what is our mission in this talk? It is basically, as I mentioned before, to learn deep neural nets from minimal supervision. So we are going to basically play with two ideas. Idea number one, we are going to inject prior knowledge as structural biases into our model. So what we are going to do is to impose these prior knowledge as a structural constraints into the learning algorithm to train the model, or training algorithm to train the model. And the other idea is we are going to investigate designing models which can learn different tasks at the same time, right? And our hypothesis is that learning knowledge from the other tasks will help learning the main task better. And these two ideas actually resulted from 2 6-week workshops that I co-led in 2015 and 2017 in University of Washington and CMU. All right? Questions? Good. So, idea number one. So, idea number one basically is about injecting our prior knowledge into the either architecture or the learning algorithm. And I'm going to do this for a specific problem that I work with, which is neural machine translation or machine translation. Think about Google Translate, right? So translating by machines from one language to another. So the basic idea of the neural approach to tackle machine translation is that is the following. So suppose you have a foreign sentence. You use a neural component which we call encoder to read the sentence and map it to a canonical space, and then we design another neural component which we call the decoder to read off and generate the target sentence or the target translation from this encoded input, right? So in other words, we are going to map a source sentence to a language independent concept space and then map back that thing to a language of interest in target. All right. So this is an example of how we do it. Suppose I have a sentence, whose words are x0, 1, 2, 3, 4. So specifically for those of you who are familiar with neural networks, we have a recurrent neural net to read this sentence. What we do then is we start from basically the first position in the target sentence and generate the words in the translation one by one from left to right. And when we generate each of these words, actually we look at the different parts of the source sentence, right? In other words, this is similar to how human translator basically work. So when I want to translate, right, so I look into different parts of the sentence to basically attend to different parts of it to be able to generate my next word or phrases. So this is exactly what our model does. And this layer that you see here is that concept level representation that I mentioned before. You can see that this concept level representation of the source sentence is doesn't have a fixed size. So depending on the length of the sentence, the length of the mapping in the concept space can change. All right. So the decoder component as I mentioned, attends to different parts of the source of the concept, and generates the words one by one until it stops the generation. All right. So, what I'm going to talk about is an important byproduct of this of the decoder. So imagine that this was our source sentence and this was our target sentence. So for each for the generation of each word in the target, what we need to do is to attend to different parts of the concept, right? And then this vector actually shows that attendance vector, or the probability of looking at different parts of the source sentence when you generate this target word. Similarly, this is the attendance vector for the next one, and so on and so forth. So did I mix up? So this is the source, this is the target, right? So for each word in the target, the row here shows how much important was a particular word in the source when the decoder generated this particular word in the translation. What's the importance of this table that technically we call the alignment table? The importance of it is that we can inject some prior knowledge through constraining this alignment table. All right. So what kind of constraints? So these are the three constraints that we have injected. So the easiest one is the symmetry, right? So when you basically translate from a source sentence to its translation, the target, and when you reverse the translation direction, right? So the alignment table should be symmetric, right? So in both directions, pair of words which are translated translation of each other should have high attendance in the alignment, high value in the alignment table. So I'm not going to talk about the other properties and that we can actually use to constrain this alignment table. Just look at the symmetry one. Right? So, if this is your source and this is your target, and if you change and consider this as a source and this as a target, these alignment tables should be, transposed of each other. I try to not talk about mathematics, but I couldn't help myself. But essentially, what you can do is to basically train the two models in both directions, and then require the alignment table of these two models to have this dependency to each other, right? And then once you've done that, in the training objective of your model, you have a term for for changing the parameters of this model to make it good, another one for this one to make it good, and then another subject to a constraint, which is this that we talked about, and that makes the optimization, the two terms in the objective function couple together, and coupling helps each of them to basically learn better. All right. Some very brief presentation of the results. This is a task for Chinese to English translation. And what I'm showing here is, perplexity. Perplexity is, think about it as the loss value. So the lower is the better. So this is the the original model, which that doesn't use any of these constraints, and it has this perplexity. And this is another version of the model which doesn't have any constraint in it. It has it's a basically improved version of the very naive model that. I didn't talk about the difference between these two, but it is not important for us. So what is important is basically these lines, which show as we add more constraints into the training process of this model, we make it better and better and better by reducing the error further and further and further. All right? And this work has been used in other for other problems as well. For example, in speech-to-text translation, for which the data is not abundant, my colleagues have used this to improve the performance of their system. All right. So I'm going to focus on part 2, which is sharing the knowledge of different tasks to help a better learning in one main task that you may care more about. All right. So far, probably you have understood that the task of interest for us in this project is machine translation, right? So what I'm gonna do here is to leverage the knowledge of other tasks to make machine translation's performance better, right? So I have in this scenario, for the language pair that I'm interested to build a translation system for, I don't have enough, training data, right? So I'm going to show you, the 2 language pairs that we've considered. They are English Farsi and English, I don't remember the other one. So what we are going to do is to basically share the knowledge from other tasks and with this task and see whether we can do better in translation. So what are the other tasks? So we have experimented and investigated the use of several other tasks. One of them is syntactic parsing. So for those of you who are not familiar with your language technology, syntactic parsing is the process of mapping a sentence to its syntactic tree. So it's a mapping from a sentence to a tree. So your input space for this problem is the space of sequences, and the output space is the space of trees. And you are looking for a function, for a model to map sequences to trees. The other task that we have investigated is semantic parsing. So in semantic parsing, what we are basically interested in is to represent, the essence of the knowledge conveyed in a sentence by a graph, right? So essentially, it's a problem where the input space is the space of sequences and the output space is the space of graphs, all right? And we have investigated other problems as well, but I just wanted to highlight the use of these 2 here. All right? Now, if I were to solve each of these tasks independently, I would do the following, right? So for machine translation, to translate a source sentence to a target sentence, what I would do, I would design an encoder-decoder architecture where the encoder reads the input sentence and basically spit out the translation of that input sentence. If I were to design another neural model to solve the semantic parsing problem, what I would do, I would design again an encoder-decoder model where the encoder basically reads off the input sentence and spit out a graph. And similarly for parsing, I would design an encoder-decoder architecture where the encoder reads the input sentence and spit out the syntactic tree of that input sentence. All right? What we are going to do is basically to couple some components of these different models for solving these different tasks. More specifically, I would be able to share the parameters of the encoders of these 3 systems, right? And only, in other words, I only train for one encoder, which reads in, sentences for these different tasks, and then I let each of these tasks to have its own, a specific decoder to spit out the output. So this yellow thing basically simply means that, I only have one encoder in this multitask learning architecture, right? So that basically shrinks the number of parameters across all of these tasks, and essentially learning, from learning theory perspective, learning an improvement in the learning happens because of that. Is it clear? I can do, the same thing for the decoder part, right? I can let, each of these tasks to have its own specific decoder and basically couple together the decoders, right? Or something which is more ambitious, I can design only one model, one encoder-decoder, which can do all of these tasks, right? Which actually we did. All right. So this is, I didn't have enough time to make beautiful, graphs to show the results. Sorry about that. But this shows, the interesting results that we've obtained. So the tasks are, going from English to French, English to Farsi, and English to Vietnamese. Of course, we have lots of data for English-French, but we have simulated, the scarce data scenario for that language pair. But for the other language pairs, we really had, a small amount of data, right? So this row shows, the performance of the system which doesn't use multitask learning. So for each, for each language pair, look at only the test column, and for the test column, we have two quality measures. One is the perplexity, so the lower is better. One is, a measure of translation quality, so the higher is better, right? So this is the, the basic model which doesn't use the knowledge from any other task. This is the one which uses, the semantic parsing. This is the one which uses name entity recognition that I didn't talk about. This is the one that uses, syntactic parsing. This is the one that uses all the knowledge from all of the tasks, right? And this is, an improved version of this one that I didn't talk about. All right. So, oops. We have some. I have some examples here as well, but for the interest of time, I don't go into them. All right, so to conclude, I just basically presented some results, which show that it is possible to train, deep neural networks for low resource scenarios, at least for the problems that we considered here, based on these two, principles and ideas. So the idea number one is basically is that you can inject, structural biases which may come from your prior knowledge into the architecture or the learning algorithm that you use to train your model. And the second idea was that, learning knowledge, and sharing it among multiple tasks is useful. All right, that's it.
So, questions?
Did you compare for English-French, where you have a lot of resources, what sort of performance you get with low resources and your staff versus no resource?
High resource. Yeah. So that's a very good question. Actually, that's the kind of question that the reviewers asked, and in fact, we were asked. So based on some of the experiments, the improvement is less when you have more data, which makes sense, because basically the basic idea was that if you don't have enough data, how you can compensate for for the knowledge that you miss. due to the loss of due to the basically loss of the data, right? But if you have lots of data, I don't know how much of that knowledge, syntactic or semantic knowledge can be learned, but based on some preliminary experiments, we basically noticed that the improvement is less. The improvement is less in the sense that, the difference between your model, which doesn't do multitask learning and is trained on a lot of data, compared to the same model where where you consider an auxiliary task, the difference between them is not that big.
I've got a bit similar question, around comparing sort of.
Yep.
I understand because the title and conclusion was about neural networks, but the context wasn't about neural networks. So, like I understand that this neural networks goes into decoder and encoder. Now, the question is, why did you use good old-fashioned machine learning algorithms, as encoder and decoder? Or in other words, have you compared, the neural network stuff with those good old-fashioned machine learning?
There is no encoder-decoder in the good old-fashioned approach to these problems. There isn't.
Okay.
Could you explain a little bit how the encoder actually works?
Decoder?
Yeah, encoder.
Encoder.
Anyone you like. Encoder.
Sure. It's a recurrent neural net. Basically, I didn't deliberately go into the details of that. It's a standard recurrent neural net where the state of the network at time t is a function of its state at time t-1 and the input at time t, right? So you apply this recursive function, right? And then and for the time, for the first time step or time step 0, you assume that you start from the 0 vector. So if you think about what I just said, you can compute the state of the network in the next time step from its state in the previous step, which is the blue thing here, right? This is calculated from this and this, right? And then you can do it for all of the time steps, right? So the function that you have here can be a one-layer perceptron where you have in your input neurons these neurons concatenated with the neurons representing your word, right? And then you have, I don't know, n plus m number of neurons, right, in the input, and you have n number of neurons in your output. So you have a fully connected thing. You do the calculation by a standard neural network thing. However, the functions that we use here are more involved. They are carefully designed functions whereby when you want to train them, the gradient passes through a long distance, right? So if you're not careful about these functions and try to train these kind of models, right? If you compute a loss at the end and try to backpropagate the loss, to all of your time steps so that they have a say in training your parameters, then you may encounter instability in backpropagating those things because your gradient can go very big or very small. So in both cases, your system becomes unstable. These functions are designed carefully so that the backpropagation of the gradient is well behaved.
So we use gradient stabilization. We're not relying upon the block size or the time windows.
We basically we don't limit. We don't have any fixed size for the time window. So it's it's the length of the input. We backpropagate through all of the time steps.
So how was the length?
Oh, it differs. Like in different corpora, the length of the sentences are different. Like for example, you can have easily sentences between 20 and 50. You can have some sentences, with the length 100. It becomes even worse when you think about, speech translation, because in speech translation, what we do is that, we get the speech, we chop it off into, let's say, 10 millisecond, intervals. We get the MFCCs, and then let's say you have a 1 second speech, right? So if you have a 1 second speech with 10 millisecond kind of chopping, you have 100 MFCC vectors, right? And usually the speech is more than 1 second. So, they can be ridiculously long for different problems.
So you're using an MFCC?
For speech, yeah. Not for this one. No worries.
I'm wondering if you can give us an intuition why syntax works, because it appears to me, why an encoder-decoder architecture with shared encoders and decoders can work for syntax, because syntax is quite different. It generates a tree which corresponds to the source language,
yep.
Whereas the other two decoders, well, the middle one, the semantic analysis, generates some general concept graph, but the target language generator generates target language, which can have quite a different syntax from the source language.
Yeah.
Look at Farsi or Japanese or
right.
all these languages that are completely backwards.
SOV, SVO.
So how can syntax work in this unified model compared to my intuition?
In fact, syntax should work because of that intuition, right? So if, I'm going to change the gears and talk about, the good old-fashioned models where, we use in my PhD time. In those type of models, we basically, there is a definite conclusion that the syntax is helpful. And it's also intuitive, because if how to say it in short. So if you know that from the syntactic trees of the source and the target, that whenever you have a verb and object, you have to reverse them in your target language, right? You don't need a lot of data to learn this rule, right? So with just, a few amount of data, you can learn that rule, which you can then apply to, so many other situations and improve the performance for those situations. Whereas if you didn't have the syntax, right, for every combination of a verb and object, you have to learn that, if they appear in the source, they have to be switched in the target.
So you're saying you learn the more general concept that this language is backwards. So
yeah.
Starting with backwards.
Yeah. So for these ones, I'm not going to claim that, because we are not sure. Actually, looking into these models and realize and explain why syntax is helpful is an open problem, right? So far it's just empirical, result which confirms our intuition, but we don't know, really what's happening in there which has resulted into this improvement. Oh, parse it in the same language, in English. Yes. Yeah. That's a really good. So that's a really good thing, actually. And there is a paper which actually does that, and they show that it helps, right? So that's a totally valid thing to do, but we didn't actually explore it here. So that leverages the syntax in the target language. So what I presented here is everything was about the source language, but you can add that task as well to incorporate the target syntax. Okay.
So the idea of multiple task learning is very interesting. My question here is how to select the related task in predicate. Because I find using main legislative different kind of task together, maybe the performance will be different.
Yeah, that's a really good insight as well. So you have to be very careful about what we call auxiliary tasks, right? Because if you're not careful, then your main task actually can be contaminated with bad knowledge from the other tasks, right? And hence, the performance degrades. However, this happens only if your multitask architecture is the very simplistic thing that I presented here, right? However, there are some architectures which are more complicated which basically we explored those as well. That if your multitask architecture is complex enough, those situations won't happen. So even though your other tasks may have may have hurting knowledge for your main task, your main task is kind of shielded against them. So all depends on your architecture for deep multitask learning and your training algorithm. Right.
So, are there any questions from Caulfield? No? Okay, well, I guess we declare this event closed. There are some snacks apparently over in the tea room, I'm told. I haven't seen them yet, but apparently they're there. So, thank you.